So question A1, first up, we have a box that has been sliced at an angle by a plane. A plane is any flat surface, so a saw blade, we'll say for example, could be considered a plane. We have to draw the elevation and plan of this cut surface. So the surface has been cut by a plane. The traces of the plane are VT and HT. VT is the vertical trace, so where that plane would cut the vertical plane. So in other words, where our oblique plane, the angle plane, cuts the vertical plane, is the VT. HT, the horizontal plane, so where that angled plane or the surface hits the ground, is the horizontal trace. And with the way we're going to set this up is we're going to use horizontal lines. A horizontal line, for example, I'll use the 3D view. I've got a horizontal line here, HT. If I draw a horizontal line from, we'll say this corner here, I'll draw the horizontal line and I'm going to draw it horizontal to hit the vertical plane. So there it comes in. I've got this point P. So now what I have is a horizontal line. I know it's horizontal because I drew parallel to the HT, which is a horizontal line. So a horizontal line drawn from a known point, and I drew it to hit the vertical plane. You can see when it hits the vertical plane, it hits the vertical trace. So it gives me this point P on this line, VT. I can do the same thing when I come back to elevation and plan. So I take the corner here. Here's my corner. I want to draw a horizontal line in the plan view. I've got my plan view, I've got my elevation. Horizontal line, as I did in the 3D view, I came parallel to HT. So from here, I'm going to draw a horizontal line to hit the vertical plane. The vertical plane is in plan at the XY line. So I've got my line, and I'll call it, for example, 1. This was point P, 1P. I'm going to draw the same line in elevation. Now remember, point P is on the vertical trace. So all I need to do is find point P in elevation. Point P in elevation is on the vertical trace. And I know that line 1P is a horizontal line. I drew it horizontal, so it's parallel to HT. So I just come along and draw a horizontal line in elevation. 1 in plan, bring it straight up to elevation, I get point 1 in elevation. So what I'm doing is setting up horizontal lines, and I do that for each of the points. I take the other point, I'll call this 2, and again, parallel to HT, because I know it's a horizontal line. I call this 2 point Q. So 2Q, again, find my point in elevation. And again, I know that the line 2Q is horizontal. So from Q, I draw a horizontal line. And again, point 2 comes up into the elevation. And here's my point 2 in elevation. So I've got points 1, 2, and 3 and 4 are already done. I call this 3. Here is 3 in elevation. Point 4 is at the back. Point 4 is in elevation. So when I go to draw this in, I've got my cut surface. 1, 2, 3, 4. Here it is in plan. 1, 2, 3. Here's 4. Those were done already. And back to 1. So that gives me the elevation of the surface drawn in. And again, if I do 3 and 4, it was the same thing, and you can see the lines they did for 3 and 4, so it's the same process. So if I want to find a point taken from plan to elevation, I go parallel to a horizontal line, which is HT, draw the line to hit the vertical plane, and I find the same horizontal line in elevation. That is question 1 part A done. We're going to skip down to part C of the question just because it's still in the elevation and plan view. On the orthographic on the right, determine the true length of the shorter diagonal of the cut surface. Now, it looks like this is the shorter diagonal, but you couldn't be sure. To be 100% sure, you'd measure the length of the 2 diagonals. The diagonals, I'm going to highlight them. So one diagonal is 2, 4, and I'm going to do it in red with a broken line just to show it. So 2, 4 in elevation is here. The other diagonal is 1, 3. And in elevation 1, 3. So just to highlight them so we know they're different. I need to figure out which is the longer of the two. Now, we can do the same as we normally do, but it would be a little bit time consuming. In other words, if I want to find the true length of line 2, 4, I can just look in at 90 degrees, draw an auxiliary elevation. So I'll project out here, draw an auxiliary elevation. If I want to find the length of 1, 3, I project off at 90 degrees, so I draw up here, draw an auxiliary elevation. When it's just a line we're dealing with, it's a little bit time consuming, so I can do the easier version, which is rotate the line. If I'm dealing with a line, I can do this. It's only to get the length of one line. So to rotate a line, I'm going to rotate the line until it looks horizontal and plane, meaning I'll be looking in at 90 degrees to it in the plan view. So I'm going to take line 2, 4. I'm going to rotate it till it looks horizontal and plane. So I'm just going to take 2, 4 and I'm going to swing it round until it has a horizontal position in plan. So in other words, my new position of 2, 4 is here. So that's where 2, 4 ends up. So I've swung the point 4 around and down onto it. I'm just going to find the new position in elevation. So height of the points doesn't change. I'll project up point 4, get 4 in elevation. Here's where 4 is now. 2 hasn't moved, it was my hinge point, so 2 stays where it is. So the new length, or the true length that I see, is 2, 4 here. That is the length of 2, 4. It's the exact same method for the other one. So when I take 1, 3, again, doesn't matter, I can do it either direction. I'll take 1, 3, swing it to a horizontal position, meaning 1, 3 in plan now is here. So it looks like it's horizontal in plan. So that is what I'm doing. Meaning I'm looking in at 90 degrees for now. So this is where I'm looking in plan. Now I'm looking at 90 degrees. Same thing, I find the new position 3. Here's where 3 was, let's swing around to here. 3 is going to move out slightly. So in other words, it moves out just a tiny bit. Get the new position of 3. And my true length of 1, 3 is just slightly off where it was. Here's the length of 1, 3. This is the length of the shorter diagonal. So 1, 3 was the shorter diagonal. If you looked at just the 3D view, you would have thought it's the longer diagonal, but it isn't. Coming back to part B then, we have to find the points, the cut points in the 3D, this pictorial view here. We have 2 of them done, so 2 of them are done here for us, and they've given us a hint on how to do it. They've got the line coming back parallel, vertical, back out parallel. So in other words, it's similar to what I did in the orthograph projection. This line, 1P, represents the top line and the bottom line. So that's why this works in the orthograph projection view. So I can take my point here, from vertical to hit my VP, or sorry, vertical trace line VT, and then back out again. There is my point. So that gives me my third point. So again, back parallel to HT, up vertical, here's my vertical line I'm copying, and back out parallel. Same with the third one. Back parallel, vertical off my corner, this is what I'm taking as the vertical line, up to hit my VT line, and then again back out parallel. And there is my 4 points. 2 were done for me. That gives me the 4 points on the surface. I'm only darkening it in now so you can see it. Don't you darken it in, you're covering up your construction line. There is the surface. That's question A1 done. A2. This is based on 2 parabolas. Do not get confused. This is not a double hyperbola question. This is a parabolas question. They're totally different. So it shows 2 parabolas. It's just 2 separate parabolas. They're not connected in any way. So I'm just doing parabola construction here. So I'm told here, V1 and V2 are the vertices of the parabolas. F1 and F2 are the focal points. Draw the parabolas. Show clearly how to determine the position of points B, D, P, and Q. We'll get to those in a second. Okay, so as we said, this is just a straightforward parabola question. I'm putting a parabola into a box. Now normally the box would extend down fully, but basically we have the top half, bottom half of the parabola. Forget about the far side for the time being. Our parabola construction would be as normal. I divide it up. I can divide it up into 5 equal sections or 4 equal sections or whatever it is. It doesn't matter. I'm going to take my side out here and I'm going to divide it into 5 equal sections. So construction out, and I'll come out in tens. So 1, 2, 3, 4, 5 equal sections. Join back to the top. So 1, 2, 3, 4, and 5. So again, I've got my 5 divisions there. To easily go and copy those on, I just join the diagonal of the box, and I can take my point, bring it across, bring it across. So I'm coming parallel with these lines. I'll draw in one so they can see what I did. So in other words, they see that I brought that parallel. So now I've got this one divided into 5 equal points. Start from the vertex. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. One set has to go parallel to the axis, which is my broken line. So I've got my set of points. The other ones join to the vertex. And my lines. So then my points. Line 1 cuts line 1, line 2, line 2, line 3, line 3, line 4 cuts line 4. That gives me my points. It gives me one portion of the curve. All I have to do is copy that over to the far side. So if I want to copy that over to the far side, take my points across. These are the points that I've actually found, and I'll do an axial symmetry. So the actual points, not the construction lines. Take the points across. Done. That gives me the top half of both curves. I'll sketch those in. For the bottom half, it's exactly the same. So bring my points down. I'm probably only going to need 2 of these points because it's going to go off the page. This point and this point. And again, it's an axial symmetry. 2 down. 1 down. I'll do that same on the other side and sketch those. Okay, so I've got my 2 points. It's asking how to clearly find where it cuts the base point here. By just drawing down that curve, I won't find it accurately. So what I'm going to do is I see here, this distance here from B to the center is the same as from P to the center. And I can measure out those distances. So in other words, I've got my distance here from B to the center. That's my distance. I'd take the same distance up. And when I bring it across, because I've got the curve already drawn in, it will give me those 2 points. So in other words, here is where point P is, here is where point Q is. Then I can draw that line down vertically. That is my definite point at the bottom, definite point at the bottom. That lets me sketch in the curve on both sides. They said clearly indicate, so I'll show it. Distance is the same as the distance. So if they were saying to show clearly indicate, that is telling them how I found it. I measured the distance, measured the same distance, and I've shown my horizontal line coming across. Last part then, draw the circle tangential to the curves at point P. So in other words, the circle is tangential at points P and point Q. As soon as I hear tangent, I'm thinking, right, I'm going to draw a tangent to the curves. To draw a tangent to the curve, we are going to bisect the angle, and it's back to our eccentricity. I'll take F to P, which is here, P to D. D would be over here. So if this was the curve and this was eccentricity, D would be out here somewhere. It doesn't actually matter where it is, because when I'm dealing with a parabola, I've got my F to P, P to D distance. We bisect that angle. So I come along and bisect that angle. I draw my angle. And that's why I don't need point D, because I'm just going to bisect the angle. So bisect the angle there. that would give me the tangent at P. I don't actually need the tangent to P, so that would be my tangent construction. I don't fully need that. What I need is the normal to the tangent, so in other words a line at 90 degrees to that. So I had to kind of find the tangent to come back around. So I found the tangent. I need the line at 90 degrees. The 90 degrees is the normal, and I'll show why that is. When I draw in my normal, I know the normal, this line is where the center of the circle is going to be. It has to be the same distance from both, so I've got my center line here. So in other words, I come out from the normal, hits my purple center line, that lets me draw in the circle. And there's my circle drawn in. That's the first two done. Part A3. So we've got two planes ABC and ADE. Draw the plan and elevation of the line of intersection and determine the dihedral angle between the planes. So normally we're given the line of intersection. It's not given to us here.